Well, good afternoon, everybody. Happy to be here to show you guys a couple of what I think are new ideas regarding a couple of topics, and I'll go into that in a second. I worked at Shell for 30 years, and then I went out consulting, and so I have a different well of knowledge than many people that worked here in Utah their whole lives. So I see things through a different lens sometimes. Sometimes it's pretty cloudy. Sometimes it's crystal clear, but we'll see how this goes. Also, well, let me see if I can get this to work here. The remote, right? Looking on the. Gotcha. Okay, so what I'm going to cover today is a topic that has been near and dear to my heart for a long time, for about 18 years. And that is, why did the Pine Valley laccolith get in plate at that particular stratigraphic horizon within the Claron Formation? I've always said that it's a zone of weakness, but I didn't understand it until I got a regional perspective and also some pictures, some photos from Ben Everett, who had hiked up to the contact at Pine Valley, and I'll share those with you and wanted to acknowledge him. Excellent photographs. I was supposed to go with him that day and I wasn't able to. Also, I'm going to present another explanation for the regional diagenesis of the Navajo Sandstone. I know there are many ideas on how the sandstone became white within Snow Canyon and other places, but I'll show you some evidence that from regional work on another explanation of why that might have happened. And I might open up a can of worms in the process of doing that. So I'm hoping that we get some lively feedback. All right, so in order to do that, I'm going to review the tectonic history. Now, some of this is going to be just a review for a lot of you, but I feel it's necessary to get the timing down on the timing of structure, the timing of emplacement of the laccolith, the timing of the ore deposits, et cetera, in order to make this story happen. Then I'll talk about the Pine Valley Mountains and how they came to be, and then how the Pine Valley Mountains, besides being a rain shadow for the St. George area, how they impact the local geology and economics. So let's start off with the tectonic history. Our tectonic history, just summarized very quickly, starting at about the oldest age in the Navajo, I'm going to call it 200, based on the latest age dating. A couple of tectonic events, the Laramide and Sevier, creating compression on the western side of the continent. You get thrust faulting, you get subduction, and the creation of magma chambers below us right here in St. George and the surrounding areas, all the way out to eastern Utah, at least. And then we had a later extension period that created the Basin and Range Province from about 30 million. Forgive me if the ages aren't exact, but it's mine. So what happened there is you created the Basin and Range, you extended the crust, and when you did that, you communicated those magma chambers with the surface through faulting and fracturing. Some of them made it to the surface and others did not. So the Pine Valley laccolith didn't quite make it, so it's a volcano wannabe. Here's just a short animation showing what happened on the west side of the continent. You had subduction of the Farallon-Wandapuka plate, and you had a stalling when this ridge couldn't subduct below the North American continent. You started to get extension, basin and range forms, the Colorado Plateau uplifts, and you get the creation of the San Andreas Fault system. So that's it in a nutshell, compression and extension. Evidence of compression in our area, a pretty obvious one anyway, is the Virgin Anticline, right? We've all seen it. It's very prominent feature. Right here is the area of Silver Reef. You can kind of see this white outline. I don't know if you guys can see my pointer on here. No, you can't. So I'll point to it. You can see this little white ridge here. That's White Reef. And those silver deposits actually rim the entire portion of the Virgin Anticline, with the best ore deposits on the western side closest to the Pine Valley Mountains. Show you a picture of what the anticline looks like. This is a vantage point up on Highway 9, looking out the Zion National Park in the distance. You can see Quail Creek Reservoir in here. It's an asymmetric anticline. So you had compression from the west. So someone pushes me on my left shoulder, I'm going to kind of lean to the right. Same thing happened with the folds out here. Most of them are asymmetric in nature. Okay, extensional tectonics. One of the bigger features that we see is the hurricane fault right here. Okay, so you have the upthrown side and the downthrown side. The upthrown side is the western edge of the Colorado Plateau. Okay. All right, so that's it. Early compression, later extension. So how did they come to be? Well, we had this subduction and we parked magma chambers down below it here. And then when we had, I'm sorry, I'm gonna mute this here real quick because I muted. Yep, it is. So when we started as part of extension, what happened was those magma chambers started to come up to the surface, and we're not getting the animation. Let me try it one more time. Sorry. I thought they were all working. There we go. So these magma chambers started to come up to the surface when we had extension, allowing that material to come to the surface, and some of them not making to the surface, of course, which are the laccoliths. A great example of this is up on the Colorado Plateau. Here's St. George, downtown St. George. You see Tokerville and Virgin up on the lower Colorado Plateau, Fire Pit Knoll. This is what it looks like. You can see all of these lineations on the map. These are all extensional faults, and those volcanic eruptions occurred along those faults where there was communication with the underlying magma chamber. Here's another view of it. This is taken from a balloon ride. My son took this actually from a balloon ride. You can see the upthrown block and the downthrown block and the cinder cone located right along that fire pit knoll. So pretty, in an ideal world, what you'd like to see is a fault communicating with a magma chamber with a eruption right along it. We live in a pretty ideal world, southern Utah. Now here's what a laccolith looks like. This is what our area looks like, where you have a lot of pipes coming up, sills, dikes, and a laccolith. The term means basically pond stone. It was from the Greek. And Gilbert was the first one to use it, looking at the diorite deposits of the Henry Mountains. So that's the first use of the term laccolith. So how do they form? Well, when you have extension, you have this stock forming, and you hit this zone of weakness right here. Now, a lot's going on at that particular time. It's not just coming up and, it's a passive system. What you have is a stock that's sitting there. It's shedding liquid water vapor, and it's also giving off sulfur dioxide, carbon dioxide, HCl, what else? H2S. And that's combining with those waters and creating an acid flow through the formation lateral to that stock. And what happens there is you get leaching of cements in those sandstones at that time. Almost all epithermal and coralline type deposits have that pre-acid flush. And by the way, hydrocarbons also, when they're migrating, have an acidic front sitting out in front of the oil as it migrates. It's minor, but there are organic acids that are expelled from the source rocks. So as this eruption continues, you bow up the surface, and then eventually it cools and you start to get erosion, and eventually you have it exposed at the surface. And what you have are Pine Valley Mountains, which is believed to be one of the largest known laccoliths on Earth. It's about 2,950 feet thick, exposed area about 115 square miles, about 300 accounting for erosion and subsurface. Okay, max elevation about 10,365. Thinking about the age of these units, this is the iron axis sitting right here. So it goes almost all the way up to Cedar City. If you look at the ages of these particular features, the Pine Valleys are clearly Miocene. They're a Miocene age feature. The rest are slightly older, not by much, but so between 20.2 and 20.5 are some of the age dates of the Pine Valleys. If you look at the Henrys and the LaSalles and the Ubahos, they're a little bit older. So they're probably a little bit like in the upper Oligocene. So it looks like we had stretching of the crust starting from the east of eastern part of Utah, younging to the west. And there's Navajo Mountain, unconfirmed between 20 and 30 million years based on the literature. If you look at the composition of these laccoliths, the Pine Valley Mountains are a monzonite or quartz monzonite. My Boston almost came out there. And the rest of them are diorite porphyries primarily. And unconfirmed for the latest thing I found in the literature. So different compositions across the plateau. So why did emplacement occur at this level? Let's take a closer look. Let's make some observations here. Anybody want to make an observation? Not an interpretation, just an observation. Well, I need to start. Well, then all the birds are standing along a line. Anybody care to interpret that? Buried power line. Right? Okay, good. All right. I'm just trying to keep myself awake. Okay, so let's make some observations. Here's where we live in Ivins. Here's Santa Clara, St. George is right here. Red Hills Parkway sits right here, that red line, and looking north on Red Hills Parkway, this is what we see. We see red Navajo sandstone directly in front of us. In the background, white Navajo sandstone, and the Pine Valleys sitting right behind it. Okay. If you look right here, probably all notice this. This is the Claron Formation, just outcrops of the Claron Formation. And it looks like it's the pink limestone member. So here's a map. Here's the Virgin Anticline sitting right here. Here's Snow Canyon and Gunlock, just to kind of orient yourself. I'm going to look at this portion of the geologic map. That's what it looks like. And all of these little TCs, that's all Claron Formation. So all those are pretty much the pink limestone member of Claron Formation. Okay. So again, we'll ask the question, why did emplacement occur within that part of the Claron? Well, what do we know about the Claron? Well, we know that it sits at the top of the Grand Staircase, right? If you're looking north from the Thebe Overlook, you can see the pink cliffs off in the distance. That's the Claron Formation, right? Anyway. We also know, or we think we know, that most of the Claron was deposited within a lake type setting where limestones will be deposited. I think this map needs to be updated because in our musings around Utah and Nevada, Claron Formation extends a little bit farther to the west than this map shows, especially Gold Strike. So here's another look at the contact between the Claron and the monzonite sitting right here. That's right. I think Ben would agree that it's close to the top of the pink limestone member. This is one of Ben's photographs. So he went up there and took some photographs and brought them back for me. I was very, very appreciative. You guys all know Ben Everett? Yeah. Great geologist. So here's the contact. Right at the top of the Claron. So here is close up. I don't have a scale for this particular photo. I imagine it's camera would be about that big in here, but I'm not for certain. But you can see it's an irregular contact where the Claron and the monzonite meet. And it looks like the magma appears to be filling in cavities within the Claron Formation. At least that's one interpretation. Not a dinosaur footprint. Okay. Here's another picture that Ben provided. You can see a little Claron piece within the monzonite. Here's another. So it looks like pieces of that Claron are being incorporated into the monzonite near the basal portion of the laccolith. Here's another picture where you can start to see some white limestone. Ben thought that was contact metamorphism, which is likely, or we might be getting into the portion of the upper upper portion of the pink into the white. Here's another picture of that as well. So this could be the top of the white, or it's just metamorphic. He said it was pretty cooked. So just a summary of the observations here. It looks like the Claron Formation is within, the laccolith is within the Claron. The contact is irregular and there are pieces of Claron incorporated within it. Okay, but we have to ask the question again, why did emplacement occur at that level? I think there's a technique in corporate America called the 5 whys. You keep asking the same question over and over again and trying to drill down, trying to find the root cause. I'll only give you 3 of them. I'm only going to use 3 of the 5. So in order to understand this, I think we need to travel 100 miles as the crow applies to Bryce Point. We have great exposures of Claron Formation, right? If you look at the white limestone member of the Claron Formation, we see multiple levels of cavern systems within the white limestone. So the white limestone layer near the top of the Claron has been subjected to karstification. The question is, what if we had extension and that zone of weakness was actually a cavern system within the Claron Formation, and you caused uplift? That whole part of the Claron was uplifted and then eroded away. So could the zone of weakness be cavern systems within the Claron Formation? Might be alone on this, kind of like vegan cattle ranchers annual convention. I wanted to put it out there and see, just present a different idea, see what people thought, and it's an interesting concept that why that zone of weakness is there. Okay. So there's that potential explanation for stratigraphic emplacement. I guess you're probably saying, okay, Mark, are you going to get into specifics of diagenesis or what? Well, sorry. Over 7 million ounces of silver was mined from Silver Reef, right outside of Leith. And that's chlorargyrite, silver chloride, or they call it horn silver. So it's important to talk about diagenesis, what happened out there to the host rock to make it receptive to that. So we're going to talk about the impact of the PVMs. This is a great paper by Beek and Royer. That's how you pronounce his last name, 2006. He talks about the history of the mining out there, all of the ore minerals, all the gangue minerals, just every aspect of Silver Reef is contained within this one article. So if you wanted to read an article on Silver Reef, this, in my opinion, is a good one. So the silver at Silver Reef was, let's see here, there we go. So we had silver at Silver Reef. We also have a little bit of silver at the Henry Mountains, but mainly uranium and vanadium associated with those particular laccoliths. So there's an undeniable association of ore deposits with these igneous intrusive bodies, okay, in my opinion. Now, there's another theory out there that was presented in 1953 by Proctor. It says that the volcanic ash in the Chinle deposits were the source of the silver, and that they were actually redeposited or remobilized by groundwater later on and deposited in the Kayenta Formation, the Springdale Sandstone Member. That was a very early idea. It's some folks still believe that. I'm not sure if I'm a believer. I don't see any other Chinle silver deposits across the Colorado Plateau, so kind of shy away from this particular explanation. And if you look at all of the ore deposits globally, what their environment was, about 82% are from magmatic sources. The rest are from placer deposits, sedimentary deposits, and some metamorphic deposits. So it's a high likelihood that these deposits at Silver Reef are from an igneous source. So what's going on during this time? The stock is sitting down here, and if there are carrier beds, those acids, the water water acid mixture is being pumped out into those formations. And in epithermal and Carlin deposits, these deposits always show in the almost always show in the paragenetic sequence that they first experienced an acid flush, which enhanced the reservoir, making it easier for ore minerals to migrate into them. If you look at the silver deposits, they're classified, most people classify them as epithermal deposits, but you'll notice that Carlin is also mentioned in those shallow deposits. Typically, Carlins are a little bit deeper, and I'll go into the comparison of those two right here. So when you look at depth and the silver, the host and the occurrence and the acid flush precursor, epithermals are typically less than 1 kilometer in depth. Carlins can be less than 1 kilometer, but also can be slightly deeper. Silver, usually in epithermal deposits. Carlin, that's a yellow check. A lot of them are gold. Okay. The host for epithermals typically is igneous. We don't have that. It's Silver Reef. In Carlins, it's carbonates. The occurrence in the epithermals are fracture vein fill. And in Carlin deposits, they are finely disseminated. And as far as an acid flush precursor, they both have that associated with them. So prior to ore deposition, these formations receive an acid flush. Now, what about Silver Reef? Okay, we're less than 1 kilometer. We're with silver, but the host isn't igneous. It's sedimentary. So it has a little bit of characteristic of a Carlin deposit. There are fracture fills and fault fills at Silver Reef, but it's also finely disseminated as well. And they both have an acid pre-flush. It doesn't sound right. So what I'm going to call them is an epicarlin deposit because it has characteristics of both. I don't think you can just put it in one slot. It's probably a little bit of epithermal and a little bit of Carlin as they're defined. Either way, they're both associated with a magmatic source. With epithermal Carlin or Carlin types, they both have a magmatic source in most cases that I've seen. So here's epicarlin. So let's take a look at the observations that we see now. And the reason I went over the tectonic history is so that we could get an idea of timing of these deposits. So the end of compression was about 35 million years ago. So the Virgin Anticline had done all it's going to do by the end of about 35 million years ago. The age of the laccolith is 22 million years ago. So the laccolith definitely postdates the age of the Anticline. The ore deposits are probably approximately the same age as the laccolith. The Virgin Anticline predates ore deposition. Okay. It's likely that the Virgin Anticline controlled fluid flow and the distribution of ore deposits as well. These ore deposits rim higher portion, this northeast portion of the Virgin Anticline. And all epithermal epicarlin deposits, almost all, have that precursor of hydrothermal fluids that flush the reservoir and actually prep them to receive the ore-bearing fluids. So are there any other anticlinal deposits? There are a lot of them. There are a lot of anticlinal silver deposits. Here's one in British Columbia, Canada. This is the Silver Cup Anticline. Sits right here. It's surrounded by igneous intrusive bodies, Jurassic and Cretaceous. And if you look at these little pie charts, all of the gray is silver. And they're located either on the flank or along the crest of the anticline. So, and the Silver Cup Anticline predates silver mineralization. Anticline was there. These hot, buoyant fluids came in and they came up and filled in the anticline, just much like the buoyancy in hydrocarbons, only it's heat related, not density. Well, they're both density. Okay, so let's take a look at a cross section across Virgin Anticline. Here's White Reef, East Reef, and the core of the Virgin Anticline. And this is from Beacon Roar. You can see White Reef right here. The laccolith is on the west side. Okay, so that's west, and this is east. This is what the White Reef mine shaft looks like. It's pretty white sandstone, white Springdale sandstone. you go on the east side, you can see it's a little bit darker. It's not white like the east side, so it looks like the light is kind of fading into what we see over in Zion, which is the Springdale Sandstone outcrop in Zion. Once you cross the Hurricane Fault and get up on the Colorado Plateau, the Springdale Sandstone is a bell ringer. So going from west to east, you go from white to kind of not as white, and then there's a big jump. You get into the Springdale Sandstone, which isn't altered at all. So some folks think that this is bleaching by hydrocarbons. And I don't think that's what's happening here. I think we're looking at the acid flush prior to ore emplacement that actually leached, not bleached, leached the sandstone. So what I think happened here is you have extremely hot temperatures in the subsurface. The subsurface fluids mix with sulfur dioxide, carbon dioxide, H2S, and emanating from the intrusive body. And it creates that acidic cocktail that leaches the iron oxide and calcite cements from the host rock where the ore now resides, prepping it to receive ore-bearing fluids. Many of you know I'm a petroleum geologist, but I do have a model that I'm going to show that is oil and gas, but we can use this to show the timing of deposition, structuration, and emplacement of the ore. So the hydrothermal fluids are buoyant. And there we go. And they rise along faults and permeable layers that were enhanced by that acid flush. So what happens is you create the structure. So imagine this is the Virgin Anticline right here. You create the Virgin Anticline, it's got some faults along the flank. And then you provide an acid flush along a fault or any kind of permeable pathway. And then behind it comes what my economic geology professor used to call the goodies. Come in after it, the silver. Okay. Let's see. All right. So when you look at the Virgin Anticline and you extend up the actual Springdale Sandstone, at one time it sat above there and now it's gone. So it's likely that a lot of the silver ore has been eroded away across the Virgin Anticline. So you know where to go panning now, right? So was the Springdale the only unit that was affected by this pre-ore deposition flush? Take a look at the Navajo. So this is just a Landsat map here, the PVMs sitting right here. This is Snow Canyon. You have the white rock. You go over to Gunlock. This is what the Navajo sandstone looks like in Gunlock. These are pieces of the sandstone in Gunlock. And if you take them, you can break them in your hand. There's very little cement holding it together. They just break up. They're very friable. There's really very little holding the sandstone together. And I challenge anybody to try the same thing with a couple of pieces of unaltered Navajo sandstone. It's very, very hard. This is almost cement-free. Okay. Go to Snow Canyon. You can see the white to red transition going from north, closest to the laccolith, going to the south. We've all seen this. We all know and love Snow Canyon, and we've observed this. Okay. Then you go over to this area, which I showed you before, where you have the white sandstone rimming the southern side of the laccolith. Come over here to Yant Flat. You've all been out to Yant, right? Plenty of signs of fluid flow running through this sandstone. It's not concordant with bedding, but nevertheless, you see evidence of fluid flow there. And then if you go up I-15 and look at exposure to the Navajo, see how this is all white sandstone sitting up here. It's highly fractured as well. So when you look at this area, what I think is happening is that you have fluid flow and you create a epithermal diagenesis zone around the southern rim of the laccolith due to fluids, hydrothermal fluids, leaching out all the cement in the Navajo. Where the iron go, well, we see it everywhere. We see bedded iron deposits, these deposits right here, and we see tons of those as well. And all the ridges are capped by a very dark layer of iron-enriched Navajo sandstone. This is from Marjorie Chan and Greg Nielsen's work back in 2009, I believe, yeah. And you can see the white sandstone at the northern edge of Snow Canyon coming out to the south where the primary sandstone is, but you can see the enrichment and where all that iron went from the sandstone as it was leached to the south. So that's what I think about the Navajo in Snow Canyon and around the entire southern edge of the laccolith. Now, after presenting this and then taking people out in the field, people always ask me, well, Mark, where's the laccolith in Zion? There's no laccolith here. This is at about a few hundred feet. Plenty of snow melt coming down, cold water, carbon dioxide sits in it and actually leaches out a lot of the iron carbonate cement, iron and carbonate cements in the Navajo. I just think this is simple chemical weathering of the Navajo. And the reason I say that is because when you go into Zion National Park along the Riverside Trail, everybody knows where this spot is. It's about halfway to Temple of Sinawava. I'm sorry, to the Narrows. What you see are these blocks of rock along the trail. And these are not Navajo. They're not Carmel Formation, not Kayenta. They're actually all of the eroded material, dissolved material that precipitated out in the canyon along fractures that has fallen down close to the trail. The rangers call it tufa. It's not tufa. It's actually all of that white, all that cement that has been eroded away from the top of Zion Canyon and is now sitting in blocks that have fallen along fractures into the canyon floor. There's another one. Looks like an alien. Kind of. Okay. Oh, so instead of didn't come out, instead of bleaching, which is the reduction of iron from ferrous iron to ferric iron by reducing fluids, commonly hydrocarbons. The hydrocarbons can do it, reducing agent. And then if that happened, the iron was dissolved away and transported away. Instead, I think a lot of this might be due to leaching and just dissolution and transport of metals, salts, or other compounds by chemically reactive fluids. Based on what I've seen up at Leeds in the Springdale Sandstone and in Snow Canyon as it rims the southern edge of the Pine Valleys. So this diagenetic alteration can be due to nearby intrusive bodies, can be due to chemical weathering, or possibly hydrocarbon migration. I know when you go over to the San Rafael Swell, Navajo Sandstone is white, right? And there's hydrocarbons bleeding out of it. It doesn't mean that it's a sprung trap. It could mean that it's a charge limited system and it never filled. Doesn't necessarily mean that it's sprung. So in order to say, from my experience as a petroleum geologist who explored a lot of hydrocarbon deposits around the world, seeing hydrocarbons doesn't mean that something was filled and spilled. You've got to look at the source rock, make sure that it's mature, make sure it's rich enough and thick enough and that it expelled in the right direction to fill the traps. And that requires a lot of work. And I haven't seen many oil companies out here exploring. It's either because it's all sprung. I know that at one time there was a paper that was proposed that the whole Escalante area Zion was one big trap, mega trap that got sprung. In order to say that, we've got to see where the source rock is. We got to see that it's mature. We have to make the right fetch maps to even see if hydrocarbons would migrate into that area before we could make those kind of statements, blanket statements that about hydrocarbon migration and sprung traps. So we looked at the tectonic history. We looked at the PVMs, why they might have been placed at that stratigraphic level. And we looked at silver in Leeds and the diagenesis across the area due to what I think is hydrothermal fluids migrating through the Navajo. And with that, I will stop and say, fini.